Hello and welcome back to another episode of Math with So. And today we're going to be doing radical form and exponential form and transforming between the two. So if you are provided with an exponent that is a fraction, all right, they call those rational exponents. Yeah, rational exponents. You are welcome to rewrite it like that, where the number on the bottom is the root and the number on the top is the exponent. There is another version of this. This is my favorite one, like what I just did. But there is another version of that is sometimes more useful, depending on what you got. So, for instance, if you had no calculator, there are other ways that you can do it. So here, you could also represent this as the fourth root of x, and then you can quantity to the third power. All right, so that's the other version, which I don't like writing that. Parentheses are annoying, but it does have its merits and its benefits, okay? Here, we're just going in reverse order. We got 7 and a third right here. We would have to do a 3 over 7. So the bottom of the fraction is the radical x, the index of the index of the radicand. That's a lot of words for me to say. Let's just do another one. 9th root, y to the 4th. All right. Here's an example where you might want to evaluate, and if you don't have a calculator, evaluating that would be really annoying. So if you write this, the first thing we got to recognize is any negative exponent should go from wherever it's located to the bottom of the fraction. So we're going to bring this 32, and it'd be positive 2/5. Okay? So if we bring that down, positive 2/5. Now from here, we could rewrite this as 1 over the 5th root of 32 squared. Now let's say you don't have a calculator. I don't know what 32 squared is, but I do think that I could simplify the 5th root of 32 into a whole bunch of 2s. 2s and 16, 2 and 8, 2 and 4, 2 and 2. 1, 2, 3, 4, 5 2s, which means they would all go on the outside of the radical. So this would end up being 1 over 2 squared, because that squared, remember, it could go here, but it also could be written as that, where it's the 5th root of 32 quantity squared. So this is really just a 1 over 4. Ta-da. All right. Here we got the 1 over the cube root of 125 to the 4th power. Now you are welcome to do 125 to the 4th power in your calculator and then cube root it. But I happen to know that the cube root of 125, when broken down, ends up equaling just 5. So this is going to be 1 over 5 to the 4th power. Okay? Now you may not know what 1 over 5 to the 4th power is, but you could resort to a calculator if you needed to, but a lot of times people just stop there. I believe, I don't know what 125 times 5 is. 725? So 125 times 5, 625. So final answer, 1 over 625, which would be what 5 to the 4th is. All right. Well, what are we going to do here? We got x to the 1/8 times x to the 5/6. This one, you could do, if we wanted to just rewrite it, this would be a little weird. It'd be 1 over the 8th root of x times the 6th root of x to the 5th, which sounds fun, but there are other ways to do it. If you have, and we're about to learn, what are the operations with exponents, maybe we'll just pause here because this looks wrong, doesn't it? You could put a 1 there, but you don't need to. So what do you do if you have exponents like number 2 here, where we're sitting next to each other, and you have a to the 7 over 4 times a to the 5 over 4? You would have to multiply the numbers, but there are no numbers, but you would have to add the exponents. Remember, with examples, let's do it up here. Remember, like x squared times x to the 3rd equals x to the 5th. You would add them. Versus x squared times raised to the 3rd would be x to the 6th. So here we add, and here you multiply. So in this case, we have to just add 7 over 4 with 5 over 4. And if you add 7 over 4 with 5 over 4, because they have that least common denominator, you end up with 12 over 4. 7 plus 5 makes 12 over 4, which of course is a to the 3rd. 12 divided by 4 makes a to the 3rd. Okay, what about over here, where it's an exponent raised to an exponent? Remember, we multiplied versus add. So in this case, We don't need a least common denominator. It would be b to the 3 over 12. When you have multiplying fractions, you just multiply the top number and multiply the bottom number, which makes b to the 1/4. Which brings us back to number 6. Okay, for number 6, we originally decided to move it as 1 over the 8th root of x to the first times 6 to, well, that just seems silly, doesn't it? But now we know that we can add the exponents. What would happen if I added, with my fraction button, of course, because I don't want to have to do this without it, 1 over 8 negative with a 5 over 6. You end up with an x to the 17 over 24th power. So that's another version of an answer. All right. Well, what are you going to do if you have values like this, where it's the cube root of 250 times the cube root of 668? As long as they are both cube roots, you can multiply the values on the inside. So we can multiply 250 and we can multiply 68 together. 250 multiplied with 68, I added them in my calculator, and you get the cube root of 17,000. That is a big cube root. All right. Well, that's one option. The other option you could do is say 250 to the 1/3, because there's a little invisible 1 here, multiplied by 68 to the 1/3. Okay. And in that case, they are not like terms. 250 and 68 are not like terms, which is why doing this, we can't just add the 1/3 and the 1/3. Here, it was an A and an A, so you could just add them. Here, the thing that they have in common is the 1/3, so you can't add the 68 and the 250, but in here, in the radical form, we could multiply them. So we could do that. And I want to know, I'm just curious, what is the cube root of 17,000? So I'm going to see what that is in my calculator. It's really big. It ends up equaling a decimal. So if we decided to break this down, it would take a lot. You could break it down into like 2 and 8,500 and keep breaking it down and simplifying it. But for me, for right now, for our intents and purposes, I think that that is a better form of the answer for right now. All right. Number 4, we got y to the negative 3/5 times a negative 1/4. When it's raised to another power, we multiply these two guys. Now, I do not want to move this to the bottom of the fraction to then deal with the negative 1/4. I can multiply these right now, and I would end up with a positive 3 over 20. Okay? Number 5, we got square root of 64, x squared, times square root of 24, y to the 4th. You have options. You could turn this into an exponent. You could turn this one into an exponent. You could, because they're both square roots with a little invisible 2 here, multiply everything together as is. You also could simplify in advance, and I think that might be the better choice, because the square root of 64 is 8. Hopefully we know that. And then 2 goes into 2 one time. Okay, so that was nice. And now I could simplify the 24, which 24 I would have to break down 2 and 12, 2 and 6. And if I break down the 6, I do end up with a 2 and a 3, which doesn't help me. So I'm just going to circle the 2's, because the 2 and 3 don't pair up. So they're going to just multiply back to become that 6. So we have a 2 on the outside. 2 goes into 4 perfectly 2 times. What do we have left underneath the square root? Well, we would have left not what I just circled, but I shouldn't have just circled them. They would multiply back to become a 6. Sorry for the multicolor answer here. Well, is there anything else we can do? Well, we can multiply these two things, because we can multiply what's on the outside with what's on the outside, which means we can multiply 8x with 2y squared, which makes 16x y squared, square root of whatever we have, which was just a 6. All right? So, last one, y to the w to the 1/2 times w to the 3 over 8. I am going to upgrade this problem slightly. I am going to say that this is 2w to the 1/2 times 3w to the 3/8. Just to demonstrate what would happen if there is a number in front. If there's a number in front, you do not add them, you multiply them to make 6. And then we would add 1/2 and 3 over 8s together. If we add 1/2 with 3 over 8 together, you end up with a w to the 7 over 8's power. So without the problem, the 6 wouldn't exist without the adaptation of adding the 2 and the 3, but I just wanted to demonstrate what would happen in that scenario. All right, that's going to do it for this one. Until next time, everybody, stay positive, and I will see y'all later. Bye.